Hello, I'm Will Carne.
And I'm still Connor Durkin.
And welcome to M1, or Mechanics 1, as we push the boundaries of maths to begin to venture into the peculiar and perilous planet that is physics.
This video has all you need to know for an A star, but if you have any questions, you're more than welcome to ask in the comments down below.
Or Facebook, facebook.com/Swahey Productions.
Or if you're feeling really adventurous, try Google+. It's good. We've been sponsored. Do it. Do it. It's beautiful. It's elegant.
They have our families locked up. In this first video of safe. This one we're doing turning SUVAT.
So let's begin with the latter.
Yes, SUVAT.
Latter-day Saints. Not the Jehovah's Witnesses.
Let's just begin with moving graphs. At A level, we distinguish the difference between scalar and vector. A scalar has only magnitude, like speed, whereas a vector also has direction, like velocity.
Distance is scalar, whereas displacement is a vector. You may be displaced 1 metre west from your starting point, but you may have travelled a long distance to get there.
As speed is a rate of change of distance and the magnitude of velocity, then velocity is the rate of change of displacement given in metres per second.
Now, you should know that speed equals distance over time, but as direction is involved, then finding velocity is a little more difficult, so you need SUVAT equations, which we'll come on to in just a mo.
Acceleration is the rate of change of velocity. See how it's all linked?
Rate of change of things going on.
We love it. We love it. Now it measures the amount that velocity changes each second. Therefore, it's given in meters per second squared.
You can find the acceleration, therefore, with the change of velocity found by taking initial velocity u from the final velocity v divided by the time taken.
Now, you need to know how to draw graphs of displacement, velocity and acceleration all against time.
We're going to use the example of throwing a sheep, called Sean in the air.
Very original.
Very original.
Right, its displacement will increase, we should say. He's a person. His displacement will increase from its starting position until it reaches the top of his flight, where gravity will cause him to start coming down. Here, his displacement will return to the axis, which in our scenario is the ground. Portion on the sheet.
It's okay, we'll put a mattress under him, he'll be fine. His velocity will start high as you throw him, but he will slow down due to the force of gravity, which is an acceleration upon a mass.
Then, as he returns, his velocity will increase again due to the acceleration due to gravity, but it is in the opposite direction to the one that we're taking as positive, so on a graph it's negative.
Finally, acceleration, which is what we said the gradient velocity graph, as you can see in this case, is constant.
Its acceleration due to gravity is about 9.8 meters per second squared in this scenario. It's negative in this case because of the direction that we're taking the positive.
Yeah, we just assign positive being up and negative being down. You can do it either way, it just makes sense. As they are rates of change, you can use differentiation and integration to find one from another.
So differentiate displacement to get velocity, differentiate velocity to get acceleration.
And integrate if you want to go the other way.
This is C2 knowledge partially, and most of this is actually M2, but it's a nice concept to get your head around.
Get it out of the way early with.
Yes, and if you're asked to draw a speed graph, then that's very easy. It's just velocity, but always positive.
Well, hey, and the last little bit of info before we move on is acceleration due to gravity.
We briefly mentioned it, but here's a tiny physics lesson
for physics
with Dr. Connor Durkin.
Hello there. Sorry, that's my doctor voice. It's not a very good one. Essentially, gravity is the phenomenon causing all bodies to attract to each other with a magnitude based on the object's masses and distances between them. Now this is A-level physics. All you need to know is that due to this force of attraction, the objects are accelerated towards one another. So
Sean the sheep near the surface of the Earth is accelerated towards the Earth with acceleration g, little g, where g depends on the size of the masses.
Near the surface of the Earth, it is 9.8 meters per second squared. It should be 9.81, but this is maths, so they're less accurate.
And all you need to know is that acceleration due to gravity g on Earth is around 9.8 meters per second squared. But it's nice to know a bit of physics.
Lovely to know.
And finally, a little note of warning. In maths, we don't like reality, so we usually ignore all other frictional forces like air resistance.
Because it's just too complicated.
Yes.
Moving on to our favourite part of the unit, SUVAT. Oh, lovely stuff.
Oh, actually... So
don't worry, you SUVAT.
No, but you see, if you're describing motion with constant acceleration, then you do use the SUVAT equations. But we, here at Wave Productions, we call them STAVU.
Yeah, STAVU.
Stavel.
Yes, not Savile, let's not go for Savile. No. Right. The S stands for displacement, the T for time, the A for acceleration, and the V for final velocity. Or as it's written here, vinyl velocity, because William's so funny at writing scripts.
No, it is the vinyl. No, it's meant to be like that. It's vinyl velocity.
It is vinyl. No, but the Germans say vinyl. No, they say.
No, it's meant to be that because it's S for displacement, T for time, A for acceleration, V for vinyl velocity, and U for velocity.
Velocity?
Right,
that just doesn't make sense.
The acceleration is given by V minus U all over T, which can be rearranged to get V equals U plus AT.
The displacement is velocity integrated, which gives simplified half U plus half VT.
Now you can combine these to get S equals UT plus half AT squared, and S equals VT minus half AT squared.
Then a bit more rearranging and mixing gets your last equation, which is V squared equals U squared plus 2AS.
These are given the exam.
Really?
No, they're not. You have to learn them.
Oh, that was me.
It was quite mean.
Cruel.
Now, the best way to learn them is like this, where you identify the variable you are missing in the equation.
I go about that question, well, we both do, by writing SUVAT and then, down the page, and then writing which variables we have, putting a question mark next to the ones that you don't have, the one that you want, and a cross by the one that isn't relevant at all. Then from your head, you pluck the formula that doesn't need the crossed variable, and there you go. You SUVAT or Stavu away.
Stop SUVATing.
SUVAT.
It's
SUVAT,
Stavu. We're trying to create a brand here, Connor.
Vutua.
And let me say one more time, if the acceleration is not constant, then they will not work.
That was almost seductive. So as we said, moving on to vectors now, just in case you're wondering. So as we said earlier, vector quantity has magnitude and direction, where scalar only has a magnitude.
Yes, now in M1 we represent vectors graphically, either by diagram or on a classic graph.
Classic. If we're using a diagram, then we represent vectors as a force or velocity with an arrow pointing from the object. Yeah. From an object.
Yeah, like force or velocity. If we're using a graph, then we represent a vector in terms of its components x and y. We're effectively representing all vectors by displacement on a graph with a directed line segment.
So just a line with an arrow on it.
Yes, it's the posh lingo, Connor. Onto the notion of vectors.
No.
Notation, not notion. Onto the notation of vectors, the bit that stands them apart from normal algebra.
A vector from A to B can be shown as AB with an arrow on top, whereas the distance between would just be AB.
Yeah. You can label a vector with a single letter. They will use a bold letter, but you should underline it as it's much clearer.
Yeah, boldness, and you go through the paper, it's a mess, and then you write on the other side of the paper. It's chaos. You just don't do it. Yeah. But that is only the name of a vector. In the same way that you only have line y, which has an equation mx plus c. You need to be able to write down the nitty-gritty nature of your vector, and there are two ways of doing that.
First way is column notation, which you should be able to use from GCSE translations.
The top number represents the vector's x component, and the bottom number represents the vector's y component.
Another way is in terms of i's and j's, where I and j are like labels representing the x and y components of the vector.
Just so you know, they will usually tell you what I and j represent. Usually I is just going east or positive x value, and j is positive y value.
Yep.
Magnitude of a vector is shown like this. If you've done C3, you will know it is effectively the positive value of whatever the number is, or the size of it.
Yeah. The only thing you need to get your head around with vectors is that for two vectors to be equal, they have to share the same magnitude and direction.
A few little things you probably should know. A zero vector has zero magnitude, so its direction is undefined.
The vector minus a is the same magnitude as a, but in the opposite direction.
Ka is a vector parallel to a with magnitude k modulus a.
Yep, and the unit vector is a vector with a magnitude of 1, usually labelled with a little hat.
Lovely hat. The unit vector in the x direction is called I. The unit vector in the y direction is called j.
See, that's the notation we mentioned earlier. It works because they're unit vectors, which becomes clearer the more you think about it.
Yeah. To add vectors, you find the resultant vector or the vector sum. Graphically, you always draw vectors so that if you want to travel along it, you travel along the direction of the arrows from start to finish.
We tend to use double arrows to show that if it's the resultant of two vectors.
And luckily, vectors follow the same rules as you're used to. So p plus q equals q plus p, and p plus q in brackets plus r equals p plus, and in brackets q plus r. And subtracting a vector is the same as adding a negative.
Yes, now if you have them in ij form, then you can almost treat it algebraically, adding the I terms and j terms separately. In column form, add them by row.
Now, one key thing is the Wahey Productions Triangle of Truth. For vector f, resolving it to horizontal and vertical components like so. This is very helpful in real-life situations, especially with forces in the next video.
A position vector, in this case OA, describes the position of a point A relative to an origin O. So OA is a position vector of A.
They are useful for real-life situations, as a positive vector can be displayed on a map/graph where the origin is the origin on the map.
Yeah.
O.
Okay.
Yeah.
Instead of saying, in this case, that A has a coordinates AB, you say it has a position vector, AI plus BJ.
BJ. For a point moving in 2 dimensions with constant velocity, its velocity vector tells you its displacement in each unit of time. So its position vector RT is given by R0, its initial position vector plus VT.
Similarly, its acceleration vector tells you the change of velocity in each unit of time. So its velocity vector is given by its initial velocity vector plus AT.
Then it turns into a SUVAT problem. If the acceleration is constant, then you can use all your SUVAT equations except the ones where you square u or v, as squaring a vector makes no sense.
And that's it. If you have any questions,
look at them.
Then you can ask in the comments, especially if you're confused about anything or have any tricky exam questions.
There are plenty of them out there.
Join us next time for part 2. Newton gets his groove on. Until then, happy revising.
That was the lamest outro
That was so bad. Happy revising.
Happy flighting.